Let's get started. Thank you everybody for coming this week. We are welcoming Tianxiao Shen, who is a graduate student at MIT, and will be presenting some work on language style transfer. Thank you.
Thank you. Hi, I'm Tianxiao. I'm a PhD student at MIT CSL working on natural language processing and machine learning. I'm very glad to talk about my recent research on language style transfer. We know that language has different styles. We can express the same meaning in many different ways. We can say it's simple or complex, formal or informal, polite or impolite, and different people have their different personal styles. Here's an example of the two versions of the Bible. One is the classical King James version, and the other is Bible in basic English, written for people who use English as a second language. We can see that in the King James version, the first verse in Genesis reads, "In the beginning, God created the heaven and the earth," whereas in the basic English version, it reads, "At the first, God made the heaven and the earth." So the King James version is more formal and poetic, and the basic English version is less formal and more colloquial. So can we train machines to perform this task? Given a sentence, rewrite it in another style. This is an important step towards real language understanding, so that we can disentangle style from content and manipulate them. Also, it has wide applications, such as to design personalized chatbots and to appropriately convey a message according to different social contexts. One way to approach this problem is to collect parallel data and use supervised learning. So we collect sentence pairs of the same meaning but in different styles, write them side by side, and learn a parametric mapping that takes an input sentence from one style and maps it to an output sentence in the other style. So this is like exactly like machine translation. So how people do machine translation, we first select parallel sentences in, so we have English sentences and we have their translations in, say, in French, and we train a neural network that takes an English sentence and maps it to its French translation. So specifically, we use recurrent neural networks, which is a popular model to process sequential data. So recurrent neural nets have an internal memory that captures the information of what has been calculated so far. So we have a vector represent the current state, which is successively updated given the current input and output the new state. So how to apply this to a sentence? Let's say we have a sentence, "I have seen better talks." We start from null state and apply a unit to capture the first word "I," and then the second word, and so on and so forth until the last word, and we will output a vector, which is regarded as the encoding of the whole sentence. So this recurrent unit constitutes our encoder network. Then we want to decode the vector into a sentence, which is symmetrically. We start from our encoded vector and feed it a start symbol and ask it to output. Say we want to translate "I have seen better works" to Spanish. We ask it to output the first word in Spanish and then feed this word as the next input, ask it to output the second word, so on and so forth, until we output the end of sequence token, indicate that we are done with the translation. So this network is the decoder. Okay, so now we can regard style transfer as a machine translation problem and apply an encoder-decoder network on these parallel sentences, use supervised training, so that train this model to take sentences from one style and as input and output its transferred version in the other style. So far so good. So is this problem solved? However, there's a disadvantage, big disadvantage of this approach, that we need to collect the parallel data, which is very costly or even impossible in our style transfer scenario. Say we want to transfer the writing styles between two authors, we can only access to their respective corpora. These are non-parallel. So can we learn to perform language style transfer from non-parallel corpus? So this setting is different than before. So before we have parallel sentences in two styles, but now we only have one corpus in one style and another corpus in the other style. And we want to learn the style of these two corpora and try to transfer between them. So recently, people have studied image style transfer extensively. Conceptually they're similar. They take a photograph and try to transfer it into some artistic style, say Monet or Van Gogh. So this problem in computer vision was studied very early as texture transfer, and recently people use deep learning for this problem. Can we directly apply the techniques from computer vision and apply it to language? It turns out that we have specific challenges in language style transfer. And the first challenge is conceptual. So in image style transfer, you can roughly define the style as the texture. But for language, style and content are more subtle. And we want to ensure that the transferred sentence should be semantically equivalent to the source sentence. So we want to ensure content preservation. And the second challenge is technical. So an image consists of pixel values. Each pixel is a continuous value. If you change that pixel a little bit, its visual outcome also changes a little bit correspondingly. So when you want to do image style transfer, you can try to change these pixel values a little bit, see if that matches your target style better, and then do this continue this process. But for language, a sentence is a sequence of discrete tokens. For each token, we either keep it or change it into another one. And a single token change may result in drastic effects. It may make the sentence, it may change the meaning of the sentence totally or make it nonsense. So to deal with these challenges, we propose to learn a mapping between sentences and a continuous latent space. And we further decompose the latent representation of sentences into the style part and the content part. To realize style transfer, we modify the latent style component and map it back to a sentence. Question?
And just so I have in mind, a concrete example of your doing this is that example of Shakespeare and Trump, and being able to go back and forth between those two. Like that's at the end of the day, we want to be able to do those sorts of things.
Yes. So provide any sentence you want to ask. You may ask the question, what if Trump says this sentence? What's his style?
Right.
Yeah.
And what is there? How do we necessarily know that style is completely orthogonalizable to content?
Yeah, that's a good question. So,
I mean, there are certain topics that I talk about you can only talk about with a particular style.
Yes, that's true.
I'm not
So whether style and content can be disentangled completely. It's a question, but yeah, this is so for the task itself and also for the evaluation, there are still many problems.
Yeah, no, okay, yeah,
Yeah.
that's impressive, you'll be able to do that.
Question.
Can you talk more about how this would work with sort of concepts that don't sort of exist across time? So like, what does it mean to translate Trump's style, like talking about a computer, say, into Shakespeare's style? Like, that just seems sort of like not possible.
I think actually machine learning models can provide you something you cannot imagine before, so it may give you some sentence like sense. Actually, we'll talk about later. So we actually, we'll use an example of sentiment transfer as a style, and you will see that that's more comprehensible.
Okay.
So specifically, this is our generative assumption. We assume that there is a latent style variable y, which has some distribution py, and the latent content variable z has some distribution pz, and then a sentence x has conditional distribution px given yz. So we observe two corpora in different styles. Capital X1 consists of samples from px given y1, and capital X2 consists of samples from p given x given y2. Note that x1 and x2 are not parallel corpus; they're just two individual corpus. But still, we assume that they have the same underlying content distribution pz. So actually, we here we do not make explicit assumption about what is style and what is content. We assume that these two corpora have the same content distribution, but rendered in different styles. So we want the model to disentangle these two.
Do you have a training set for that?
Yeah, I'll later show you an example.
So do you assume Py and Pz are independent?
Yes. Okay. So, as we said, like before, we want to have encoder E that maps, that infers the content Z of a given sentence X and style Y. And we have a generate G that generates a sentence X from a given style Y and content Z. Oh, here we will use sentiment transfer as an example. So if you can think sentiment as a style, you can say something about you can talk about the same topics in either a positive sentiment or a negative sentiment. So, and the content will be the topic you're talking about. So here is an example. So X1 is our sentence domain of style 1, and X2 is the sentence domain of style 2. And say there's a sentence in X1 called excellent Chinese food and superb service. We want the encoder E to map it to a content representation Z that removes the style information. So imagine some point in the Z space correspond to content Chinese food and service. And we have a generate G that can generate a sentence from a content and a style. So if you generate from the Z that corresponds to Chinese food and service, if you generate a negative sentence, you will get if you generate a positive sentence, you will get excellent Chinese food and superb service. If you generate a negative sentence, you will get bland Chinese food and horrible service. So, any question about this example? So we'll use,
Would this be difference in style, or is this? It seems like this is also difference in substances, content. Yeah.
Yeah. So here we change the concept a little bit. We want to do
okay.
sentiment transfer. So
Okay,
sentiment refers to style,
Okay.
and the topic refers to content.
Okay.
Specifically, the training set for this is that you can take all the Yelp reviews and take all the negative reviews as one style, all the positive reviews as the other style. So here you get two individual corpus which are not parallel, and transfer between them.
But you could, if in a different context, you might this might be different content, right?
Yes, yes. It
So you
depends
might-
on the data.
Positive,
set.
negative might be different. Okay, great.
So yeah, so we want the encoder E and generator G form an autoencoder when applying to the same style. So if we start from a sentence of style 1 and we get its content Z, and we generate a sentence using the same style Y1, we should reconstruct the original sentence. And E and G should form a transfer model when applying to different styles. So if we first from X1 get its content Z and generate using another style Y2, we will get its transferred counterpart in style 2. So this is specifically our model architecture. The encoder E is a recurrent neural net. It takes Y as the initial state, indicates what style it is, and take the words of a sentence one by one and output the final hidden state as the content representation Z. And as for the generator G, it takes style Y and content Z combined together and output a sentence word by word. So you feed it a star symbol, it outputs the first word, and feed the first word it just generated, you output the second word until you get the end of sequence token. As we said, E and G should form an autoencoder when applying to the same style. So we have reconstruction loss, which is the negative log likelihood of generating X1 from Y1 and it's encoded Z, and symmetrically applying to X2. So now we have a model, we have our training function. We can train a model. And after training, as we imagined, we hope E and G should form an transfer model when applying to different styles. So are we good to go now? We can apply the model we just trained to a sentence, excellent Chinese food and superb service. We get its content vector Z, and we flip its style to Y2 and generate another sentence, generate the transfer sentence. What will we get? Anyone want to guess? Okay, it turns out that we will get exactly the same sentence as before. Excellent Chinese food and superb service. So there's no copy, no transfer, just copy. But what's the problem here? We hope that we map sentences domain X1 and X2 to the same latent content space Z, so that we can transfer by first go to Z and combine another style. But actually what the model learns, it learns to map X1 and X2 to totally two different spaces, Z1 and Z2, and ignores the content indicator Y. So in this way, it can easily achieve zero reconstruction loss. And when we flip the style, it will output the original sentence. So how can we fix this? Actually, we have a constraint optimization problem. We want to find the theta star that minimize the reconstruction loss, such that the X1 and X2 are mapped to the same space Z, which means EX1, Y1 and EX2, Y2 have the same distribution. Okay, so how to deal with this constraint optimization problem? We introduce a discriminator D and tries to distinguish Z1 and Z2. So the D has this goal is to output zero for encoded Z comes from style 1, and tries to output 1 for encoded Z comes from style 2. And it tries to minimize its classification error. So when D cannot distinguish between Z1 and Z2, they have the same distribution. So if you have Z1 and Z2 totally different, you can easily get a classifier distinguish between them. if you Z1 and Z2 are overlapped, any discriminator cannot distinguish between them. Any question about this part? Okay, so the overall training objective is a min-max game played among the encoder E, generator G, and discriminator D. So E and G try to minimize the reconstruction loss, while for the discriminator D, and D tries to distinguish Z1 and Z2. The lambda is our Lagrangian multiplier. So now we have the rectified training objective, and we can try it. What will we get? Here are the results. So this we call this aligned autoencoder because we want to align Z1 and Z2 to the same space. So for some cases it does well. So it transfers great to horrible. Transfers I would never go back for the food to I would definitely go back for the food. But there are also failures. So for example, I wouldn't bother, it still outputs I wouldn't bother. And for mediocre dim sum, if you're from Southern California, it transfers it into dim sum if you cannot choose from California. So it's not that good. We can train a sentiment classifier to measure how often the model transfers the input sentence to the opposite sentiment. So so we first train a classifier to classify whether a sentence is positive or negative, and then we apply to the model's output, test if the transferred sentence has the opposite sentiment as the source sentence. And this model evaluation gives us 48.3 sentiment accuracy, which means the aligned autoencoder only changes the sentiment for about half of the sentences. So how can we improve on that? So what's the problem of this model? We said we want to, we introduce a discriminator D to align Z1 and Z2. But actually, when we generate a transferred sentence, we will first start from x1, get its content vector Z, and feed it to the generator network, which will go through this recurrent generating process, output one word at a time. So even though we introduced the D to regularize Z1 and Z2 to have the same, roughly the same distribution, their initial misalignment could propagate through the recurrent generating process. As a result, the transfer sentence may end up somewhere far from the target domain. So what we want is, actually we want to directly constrain that on the output sentence. We want that the transfer sentences from style 1 should match example sentences from style 2 as a population. So for this, we introduce two discriminators. D1 tries to distinguish real sentences from style 1 and transferred sentences from style 2. And D2 tries to distinguish real sentences from style 2 and transferred sentences from style 1. And we want to train our, now our training objective become game played among the encoder E, generate G, and two discriminators. So the encoder E and generator G tries to minimize the reconstruction error, while for the two discriminators.
Are you no longer having the discriminator on your late concept area?
No, and actually we'll see that it actually strengthens the previous model. So the previous model is a special case. Yeah. So we call this model, this method cross-alignment. So specifically, we start from a sentence x1, we get its content z1, and we flip its style, get the transferred sentence tilde x1, and we take another sentence from style 2, x2, and we feed these two sentences to the discriminator. And discriminator tries to output 0 because it's a transferred sentence, and tries to output 1 because it's a real sentence. And we can then we can compute the loss and backpropagate to update our network parameters. But there's a problem here. So when we go from z1 to tilde x1, we are doing this discrete sampling process. So actually, how recurrent neural net works, at each time step, it outputs a probability distribution over the vocabulary, and you will sample a word from this distribution and feed it as the next input and continue this process. So this discrete sampling process is not differentiable, so we cannot backpropagate gradients from this. So to deal with this challenge, we use two techniques. First, we use continuous relaxation. So at each time step, we say the output log is at step t is vt. We, instead of sample a word from that, we directly feed the peaked distribution divided by a temperature gamma as the next input. So you can think of this as a soft word. When the temperature gamma goes to 0, actually this soft distribution becomes a hard distribution. So it's a continuous relaxation of this discrete sampling process. This is one technique. Another technique we used is to look into the recurrent neural net dynamics. So instead of map the output words directly, we match the internal hidden states. So if two sentences are similar, they are when RM process it, its internal dynamics should also be similar. So we match the hidden states here instead of the outputs there. So the hidden state, what's the benefit of this is that the hidden states contain all the information about the output, and it's more smoothly distributed. So this is the whole model architecture. We say this is sentence x1 and sentence x2. We pass them to the encoder E and get their content vector z1, z2. And we combine them with style 1. So for z1, you should reconstruct sentence x1. And for z2, you should get the transferred version of x2. And we pass them to the generate recurrent network and get all the hidden states. Then we feed these hidden states to a discriminator, ask them to be aligned. So we can see that this model directly strengthens the previous aligned autoencoder. So in that, the previous aligned autoencoder, we only align z1 and z2, which is the first hidden state. And now we align the whole hidden state sequence. So does this answer your previous question? Okay, so so this is our training procedure. We take 2 mini batches from style 1 and style 2. We get their encoded content representation z1 and z2. Then we combine them with the original style, and we ask the output to be the input, which is the reconstruction step. And then we swap their style, and we ask the the transferred hidden states to be matched with the original reconstruction hidden states. And then we update our discriminators by gradient descent on this adversarial loss, and then we update the encoder E and G on the loss, on the reconstruction loss minus the adversarial loss. Okay, this is kind of maybe too much. Let's see the results. So, what does this cross-aligned autoencoder perform? We can see that it does better than before. So for I wouldn't bother, it transfers to I would recommend. And for mediocre dim sum, if you are from Southern California, it transfers to good dim sum if you have Korean friends. So it still doesn't do perfectly. Again, we can measure the sentiment accuracy. So for how many sentences the transferred version has the opposite sentiment, and this cross-aligned autoencoder achieves 78.4 sentiment accuracy.
What percentage of the sentences look like sentences?
Yeah, you can ask this question. So it may output a non-fluent, non-grammatical sentence. So.
But is that a frequent occurrence? Like, are the sentences intelligible in general? Or,
Yeah, we need to evaluate that.
How accurate is the classifier?
The classifier actually on this, so we actually simplify the data set. So to handle long sentences, you need to have like attention mechanism that's more complicated. So our model is quite simple. We only have this one layer recurrent neural net. So we limit ourselves to 15 words. And for this subset of sentences, the classifier can actually distinguish very well. It can achieve 97 accuracy.
but isn't that which classifier? I thought you didn't want your classifier to be
The sentiment classifier to evaluate.
Oh, the classifier for evaluation.
So it's 97% accurate in your highly tuned training set.
Uh-huh.
But I mean, you're using it then to apply here.
Yes,
How well does it work here?
So, yeah, this number may go wrong. If you, let's say the model outputs nonsensical sentences you have never seen during your training. So this classifier trend on this original Yup data set may not apply well here. So it's only a model evaluation. There are problems here.
And your 97% classification accuracy is classifying sentences that are attached to a 1-star or a 5-star review.
Yes.
But that's assuming that all the sentences in a 1-star or a 5-star review are negative or positive sentiment, which is probably not true.
So we did.
Right.
So we regard sentences with rating 1 or 2 as negative, and 4 or 5 as positive, and discard all the 3 rating.
Right, but if you read, especially if you read a review that's a 4-star review, there's many sentences in that review.
Yes.
The sentiment of those sentences is not necessarily all the same.
Yes, that's also true.
But you're simplifying by saying that they are all the same.
Yes, we did more processing. So if you have a long review, have many sentences, you may have many statements just describing the weather today. They're not sentiment. They do not bury any sentiment. So we do another pre-processing step. We only look at reviews with less than 5 sentences. So in this case, each sentence will be more likely to carry a sentiment.
But you don't know.
Yeah, that's not for sure.
To build off on that, as an example, like for product review, you may have like a 1-star review that someone's like, oh, I loved it, it was wonderful for all these reasons, but it broke after 1 day.
Yeah, that's also
Those
true.
are all of
even
those sentences are
inside-
going to have positive sentiment, even though it's attached to a 1-star review.
We made simplified assumptions about this.
So you're assuming that doesn't exist.
It does exist, and we assume, we don't. There are problems.
So I guess I also worry that this 78% is going to probably. So is this classifier trained on the same data that you then throw into your autoencoder? Because if it is, then that's going to be probably a really optimistic measure of how well you're going to do at actually transferring sentiment, right?
Well, I think it's
Because the classifier you built to classify sentiment is built on exactly the same data that you're using to transfer style.
no, it's not trained on the transfer sentence. It's trained on the original. So you have positive sentences and negative sentences. You try to classify on that. There's no
Right, no, but that data is then just taken and put into your transfer stuff, right?
Yes, yes.
So it's using the same kind of phrases that are likely to appear in a transfer in actually building the original classifier. Like
But why that's a problem? That's
I think it probably means whether you think you're actually able to transfer sentiment is probably too optimistic.
I don't see the connection. So I think that's actually a good thing. You shoot from the same domain.
I wonder what would happen if you took some chunk of your original Yelp data, took that aside, trained the classifier only on that, and then used the rest of it for the transfer data, and then see how well it would do in that case.
I think for this specific example, it doesn't matter that much. So I use about 300,000 sentences to train the transfer model. But to train a good classifier, you don't need much. You can just, even because it's a very easy classification problem. Even if you only use like 30,000 sentences for this classifier, you can still get very high accuracy.
But that means that the classifier is really just classifying on a few keywords. And it's not actually classifying on sentiment, right? Like if it's an easy classification problem, and you don't need that many sentences, then it's implying that it's a very sparse feature set that gives you that classification, which comes down to just a few words here and there. But then understanding what that means gets tricky. So I actually think that.
Yeah, I agree. There are definitely problems about we made so many assumptions about the data. So actually now we are working on just to focus on sentiment transfer to provide a benchmark and provide more detailed analysis for these problems, for this contradictory sentiment or all these problems. Yeah, that's an ongoing research project. But here, our start point is to do style transfer, but that's kind of hard to define, and so we choose this specific case of sentiment as our style to test our model. Later we will see this model can also be applied to other scenarios, so it's only one application.
Could I ask a clarifying question? So if it turns out that all your one-star reviews are complaining about the physical space, and all the five-star reviews are raving about the food, is that because you're assuming that the distribution of content is the same in your one-star and your five-star reviews? Does that mean that it's going to decide that physical space is sentiment and food
it's
is
possible.
sentiment?
So it will change maybe some content to some physical content to the food as well, because the model doesn't know what's the difference. It only knows what's the common in these two corpora and what's the difference.
And common is sort of like a vocabulary type of common, or is it more complicated than sort of shared vocabulary or distribution of vocabulary? It's something about the actual language structure as well?
I think of it more abstractive. I think it's just underlying content, so it's not necessary just for vocabulary,
But at the end of the day, you're projecting things into some, I guess, high-dimensional space.
yes.
And which means that any sentence is that high-dimensional space you can think
So
of as its
I
own
don't know what
language.
will actually happen if you train a model on this kind of data set, but I can imagine there are more clear-cut cases. You can see what's the content and what's the style. I'll later talk about that.
Thank you.
Okay, so
Could you give an intuitive explanation of how can you combine style and substance in a way to preserve the structure of sentence, to make grammatically correct sentence?
mhm.
So I was just trying to find an intuitive way to understand how can you, avoid nonsensical sentences in your algorithm.
So because, okay, reuse this graph. Because let's say we have an autoencoder that for any sentence in x1, you map it to z, you will reconstruct x1. So this x1 is good x1, right? If all the z's coming from x2 have the exactly same distribution as this, so if z2 has exactly the same distribution as z1, you will get a right sentence in style 1 because you're trained on that.
You won't necessarily. You could have the same distribution, but you could, in principle, have a complete mismatching of any individual sentence.
Yeah. That's another problem. We'll also talk about that problem later. I think, yeah, they're asking 2 different questions.
So I guess just one minute. So the z's here are unidimensional. It's just like
No, they're high dimensional
High dimension, okay.
vectors.
Okay, but they're continuous.
Yeah, they're continuous. They're real value vector.
And do you choose the dimension?
Yeah, that's a hyperparameter.
Okay.
If you map everything into your Z space, can you visualize, like, it seems like that actually is interesting in its own right. Like, are you gonna see topics in there and stuff like that?
Yeah, that's an interesting thing to look at. We didn't do this before, but you can check what are these you learned, what they correspond, what sentences they correspond. That's an interesting thing to do. Okay. We just talked about our 2 methods, aligned autoencoder and cross-aligned autoencoder, but there are also other ways to do this. For example, you can use variational autoencoder, which is a paper 5 years ago. They do it in a different way. As we said, we want to map sentence domain x1 and sentence domain x2 to the same content space Z. One way to do that, so in our aligned autoencoder, we align Z1 and Z2 have the same distribution. But you can also impose a prior PZ. For example, you can impose a Gaussian prior, and you maximize the variational lower bound of the data likelihood, which is the reconstruction error plus KL divergence term. So basically, in variational autoencoder, you assume a prior PZ, and you align both Z1 and Z2 to your assumed Z. This is another way to do it. And here's the complete results. We tried, as we said, we tried model evaluation to evaluate the sentiment accuracy. The variational autoencoder doesn't do well. It only achieves 23 sentiment accuracy. And as we said before, aligned autoencoder has 48 and cross-aligned has 78. We also compared to a previous paper by Hu et al. Their approach actually directly aims at sentiment transfer. So they have an additional sentiment classifier to guide their sentence generation. So they achieve better sentiment accuracy. But sentiment accuracy is only one aspect. As we said, to do style transfer, we want to change the style while keep the content. If we only care about the sentiment, we can always output the same sentence in the opposite sentiment all the time, regardless of your input. But that's not what we want. So to evaluate the results of the models more in an overall sense, we also conduct human evaluation. So we ask human annotators, is the transferred sentence semantically equivalent to the source sentence with an opposite sentiment? And for this evaluation, our model actually does a little better than quite odd. So we achieve 41.6. So it means we successfully transfer the sentiment for transfers 41.5 of the sentences to the opposite sentiment while keep their content. And we can also evaluate the fluency of your output sentence, and also you can ask humans what's the sentiment of the sentence if you don't trust your sentiment classifier. We want to know that to develop an appropriate evaluation is crucial to compare these different models.
Just to clarify what we're seeing, so the fluency here, it would be like a human looked at the sentence that was put out, and I'm saying
And
like
rate from 1 to
3.2% said that's a sentence that makes sense.
No, it's rating from 1 to 4, and this is the average rate.
Okay.
4 for very fluent and 1 for nonsense. Okay, you can look at some examples. So the first line is the input sentence. The second line is the input from the previous paper, and the third line is the input from our cross-aligned autoencoder. So for input consistently slow, the other method outputs consistently good, and while our method outputs consistently fast. And for input my goodness, it was so gross, they output my husband's steak was phenomenal, while our model output my goodness was so awesome. So another example, I love the ladies here. We output I hate the doctors here. So there's still content mismatching, but you can see overall our model does better in terms of keep the syntactic structure of the source sentence and keep the content. Okay, that's all about sentiment transfer. Our model can also be applied to other scenarios that calls for non-parallel transfer.
Before you, just a quick question. So I was wondering about this model. So I'm imagining is you're taking, essentially what you're doing is you're taking a sentence and then mapping that into this high dimensional space Z, right? And then you're taking other mapping to get it back into the other sentiment. But I'm wondering what happens, or is there anything interesting that you could come from like looking at slight perturbations from that Z that you've mapped, and to see like, let's say I move a little bit from the Z that this is observed, and to see like a bunch of different sentences that are around it in the new. Like, does it just all gibber? Would it all be gibberish, or would it look like they would all kind of look similar, or is the space too?
Yeah, this is a very interesting research question. So people are working on this you want to get good sentence representations to map a sentence to a vector, so that you can easy to work to manipulate on that. But you want to get good representation so that your space Z is smooth. You can move around, or you can even do interpolation. Let's say this sentence mapped to this Z, this to this, and you interpolate between them. What will you get? So this is a very active research area. Okay, back to our style transfer. So decipherment is also a scenario that calls for non-parallel transfer. So we only see the ciphertext as corpora. We don't know what's the corresponding translations for each cipher sentence, but we want to transfer it into plain text, for example, into English. And we want to keep the meaning and vary the style. So specifically, we look at word substitution decipherment. So a word substitution cipher maps every word to a cipher token according to a one-to-one substitution key. And so to train a model, we can, let's say, take some English sentences as the plain style and take other English sentences as and apply a cipher function, and we get the cipher corpora. And we train a model to transfer between these two non-parallel corpora and see how it works in terms of deciphering. So we do non-parallel training, but we can evaluate on parallel sentences. We can compare the transferred cipher text with the original plain text and compute blue score. blue score is a measure that the highest is 100, and the higher it is, the better it is. So in this task, so we can see that the task difficulty increases as you increase the rate of substitute words. When you substitute all the words, only the cross-aligned autoencoder can do a fairly good job in terms of deciphering. By its blue score 57, all other models fail at this scenario. This is second application. We can another application is to do word ordering. Similarly, we can take an English sentence and randomly shuffle it to get and we train a model to map from the shuffled version to the original version. So this model will learn to recover the original word order of a sentence. And again, we can do non-parallel training and parallel evaluation. So for this task, it's much harder than before. So only the cross-aligned autoencoder achieves blue score 26.1. All other model fails. They are not doing better than no transfer. Okay, so to conclude, we look at the problem of non-parallel language style transfer. And the key challenge is that we want to keep the content and vary the style. So we want to disentangle content from style. We propose cross-aligned autoencoder, which constrains that the transferred sentences from one style should match example sentences from the other style as a population. There is an open question here. Even though we get distributional alignment, it doesn't imply that we are learning the right mapping. So we can learn an arbitrary mapping for, let's say, for positive sentences and negative sentences. We just map them arbitrarily. Still, we will get distributional. They look the same, but we get all the content wrong. So this is still open question. When can the distributional alignment entails instance level matching? And we apply our model to sentiment transfer, decipherment, and word ordering, which demonstrate the effectiveness of our method. And for future work, there's a lot of interesting stuff to do. So we want to work on real language style transfer. So let's say we want to transfer between professional movie reviews and unprofessional movie reviews. So there are some movie reviews written by critics, some just by general audience. Can we train a model to transfer the style so that it will turn your movie review that looks like a professional movie review? Or as the first example in this talk, we want to transfer between Shakespeare or Trump. Or we can transfer between, let's say, CNN and Fox News. They're about the same. When they write about the same events, they are in very different styles. And so another important problem is evaluation. So how can we measure that the transferred sentence preserves the content? And how can we measure it has the target style? That's very important, but it's hard to understand. And we can design better models. Our current model still have many failure cases. We may want to add specific constraints to constrain that it keeps the content words. Remember, we changed. I hate the ladies here to I love the ladies here to I hate the doctors here. We may want to identify first there are some content words that we want to keep, and then add these constraints to the model. So that's all. You can, if you're interested, you can look at our papers. Style transfer from non-parallel text by cross-alignment. It's joint work with Tao Lei and my advisors Regina Barzila and Tommy Yakola. It's last year's NIPS. And our code and dataset are available online. You can play around with it. And thank you.
So for just getting back to something that someone else brought up earlier, but for like CNN, Fox News, or Shakespeare, Trump, I mean, to some extent, there are massive content differences between these two.
Yeah.
So, or like Republicans and Democrats. Let's say you wanted to like to train something to go back and forth between them. They talk. I mean, part of the reason why they differ is because they talk about different things. And so, to what extent is I guess, yeah, this is maybe a question about this. How do you constrain this in such a way that it doesn't, that what gets picked up as style is not actually what most people would see as content?
So in our current model, we didn't explicitly specify what is content and what is style. We just implicitly assume that they have the same content but different styles. If you have the specific styles you want to change and some content you want to keep, I think, yeah, you, as a future work, you can impose these constraints on the model, into the model. Any other questions?
I think kind of following up on that, I mean, so you're calling these things content and style, but have you looked into what this, like, is what you're calling content, the Z space, actually what a person looking at it would say, yes, that's the content of the sentence and not including any of the style, or vice versa?
You mean about sentiment or other?
Sure, like your early examples you gave us with like the Chinese food and service, like you pulled out the nouns and you're like, this is the content. Have you looked at what your model's providing to see that what's being pulled out is actually what someone would call content? That's what you're labeling it as, but. Or is it just whatever's in common? Because it seems like there could be a lot of things beyond content, what someone would consider content, that these things have in common.
We did human evaluation to ask humans to look at the output of the model, whether it has the opposite sentiment and the same content as the source.
It's like one one thing you could think about is like, let's say, I mean, so I know it's like a super high dimensional object, right? So it's like maybe this isn't feasible. Let's just like the first dimension, and then give me like 20 sentences that are fixed on all the other dimensions that are just vary on that first dimension, right? And I'm going to see like, okay, this is kind of like just checking the model checking essentially, right? And just like what is the difference between the sentences that I end up seeing from that, and would we reasonably call the differences between those sentences content? Because I think you're, like what you're doing, the evaluation that you're doing is great for, whether or not the model is recovering the thing that the transfer that you want to do. But to the extent that it's checking them all at other parts, I think could be an interesting way to think about.
Yeah, you mean to check the latent representations it learned?
Yeah, because to learn a little bit, I mean, I know it's kind of black box, right?
Yes.
In this setup, but it'd be, and again, I don't know how much you can do if it's really high dimensional, but it would be interesting to know, like, what maybe some of these dimensions, the dimension with the most variation, the dimension with, you know what I mean? Like, go to and look at like what does variation on that dimension look like when it comes to actual words, or actual sentences, I guess, to see if it really does look like content.
And that's I said it's an interesting thing to look at. We haven't done that yet. Did I answer your previous question?
No. I guess, yeah. I'm just, it seems like the first step is seeing like breaking apart this process a little bit to see if what you're getting at is actually the content that you're calling it. Seems like a good kind of first.
I think for the sentiment transfer case, it's not that the sentiment and the content are not that entangled. So people are quite agreed on this. What should be changed, what shouldn't. So we have checked the agreement among our annotators. Other questions?
to me, the sentiment usually can be captured by like single words, adjectives, adverb.
No, yeah, that's some cases, but there are many hard cases.
But style is much more complicated because it's.
Yes. So that's why I say real style transfer is much more hard. It's much harder than this case. Yeah. But still, for sentiments, you can have subtle cases, like. Like you can say I there's a negative sentence. Sorry. I remember there's one example. I said I asked them to bring a new dish, but they brought me exactly the same original one. So how can you change this to a positive sentence? It's not that easy.
Another thing you might try is, there's style and there's sentiment, but there's also topic, which is probably a lot easier, right?
Why I think it's easier?
Well, because if you're writing about cars, you probably keep saying car. But if you're writing a negative review of cars, there aren't that many words that are used. You don't have to use that many words to indicate that it's negative. But no matter what, you keep saying car. So it might just be. You're shooting for a miracle here to separate style and sentiment. But you could also separate like sentiment and topic, which might be the first step.
But I don't think that's simpler. So you say when you say about car, you can say it's comfortable. You say it runs fast. I don't know. How can you change that to?
For example, here's an algorithm like search for the word car and substitute it in class. That wouldn't work exactly, but whereas for sentiment, or either sentiment or style, you'd have to change a lot of words.
But wait, what do you imagine like that previous example? I said the car is very comfortable. It's huge space and it runs.
Well, the house.
How will you change it to about the food to describe the food? Comfortable? Or?
Yeah, I bet you that would work. Well, maybe it's not easier, but maybe it's just different.
But that's interesting. Yeah.
But it'd be the same technology.
Yeah, maybe.
Maybe.
Yeah, how to transfer the topic is also interesting question to look at.
All right, thank you.
So the sentence